Welcome to Lab 3. This is another multi-week lab, so definitely make sure to start early. It is all about hash tables, so remembering those from CSCI 41 and then studying them a bit more now that we know about number theory. So we're gonna make our hash tables using closed hashing, and that is unfortunately also referred to as open addressing sometimes, which is totally not confusing at all, but now you know. Okay, so the first thing we're going to need is a new way to define a type in C++ that you may not have heard about. It is called an enum. So here's a page that you can go to look at it more. If you scroll down, there's an implementation of enum types. It's just a type that has only a certain number of elements. These are the specified things that go in the colors T type, apparently. Okay, that's all that's allowed. And that makes a type with just the things we want inside of it. Okay, it's called, enum is short for enumeration. It enumerates all the different kinds of things we want to allow to be inside of the type, if that makes sense. Okay, so let's make an enum for ice cream flavors. That's my best example. And so here's the kind of type that we want to make. We want to make the ice cream type that only has 3 possible values, right? The 3 true ice cream flavors, like vanilla, chocolate, and strawberry. Okay, and I guess technically you could use strings to represent these ice cream flavors, right? It can be like string flavor and store vanilla inside of the string, which is totally valid, but you could then go and change vanilla to something like Rocky Road or Sherbet, and it would not be one of those allowable things. That's where strings kind of break down. Okay, so we get more guarantees. You can use strings, but we get more guarantees. Guarantees with enums. It's like a better string in this case. So here's how you would define the ice cream type. You can say enum, ice cream, whatever you want to call it, and then you say in curly braces all the kind of inhabitants of the type you would like to have. So I would like ice cream to be only one of these 3 options: vanilla, chocolate, and strawberry, all with capitals. People like to use capitals for enum type values. So now I can say ice cream, because now that's a name of a type. The enum makes that type. F2 for flavor 2, set it to like vanilla or something. And it's going to make sure that it's only ever one of these 3 things. The compiler will make sure of that. Okay, so that's enums in a nutshell. We're going to be using those later. The next thing that I want to talk about is just hash tables. Let's remember what they are, what they do. It's just a lookup table, right? Taking things to other things. Keys to values, we say, right? So if we were using C++, the standard library, you could use unordered map. That's a hash table that takes your key type to your value type. And remember how to implement hash tables. It's always just an array at the end of the day that is indexable. All arrays are indexable by numbers, so no matter the key, no matter the type of keys, maybe it's a phone book, so you're storing strings as keys, you have to be able to convert that key to a number so that you can get, like, okay, John Smith maps to index 2 of this lookup table, also called a bucket, okay? Which means we need a hash function. We need to be able to hash a string, for example. That's a fancy term for convert it to a number, right? Because that'll tell us where in our hash table we can put stuff, okay? And then we have different types of hash tables because of collisions. There's different ways of handling collisions. So let's pretend that the hash function, whatever this is, took my name and John Smith's names to the same bucket, okay, to the same number index. You can't store 2 things in one index, so there's some compromise needs to be made, okay? At least at the moment, you can't store 2 things in one index. You can, option 1, use open hashing, which instead of storing values, like mapped values at an index in our lookup table, we instead store lists. So you can store a list of 2 things now, my phone number and John's phone number. That's totally fine. That's open hashing. You can store a list at each index. If you want to use the table to only store values, then that's closed hashing. And that means if index 2 is full, we better find another empty index to store my phone number, right? So that's closed hashing, and this will be what you implement for this lab, okay? Excuse me. So the idea is, well, we noticed that John's already in there. He's taking up bucket 2. We better find an empty spot for my phone number, or whoever is mapping to that same index, okay? So we have to find a way to search for an empty spot somewhere else, and there's a bunch of different ways to do it, and it's called probing. So there's a bunch of different probing strategies, we say, okay? Let's talk about each strategy, and the last one we talk about will be the one that you implement, okay? So just to keep things easy, let's pretend that we have like a reverse phone book going on. We're taking, example, reverse phone book. So we're taking numbers to names this time, which is going to make my explanation a bit easier to think about. So here's our table, and let's pretend we have a hash table that only has size 3. Our lookup table only has the capability of storing 3 things, sadly. That's okay. And then let's pretend that I want to insert my number, my phone number, and then like my cat's phone number. So I would like to, let's say that my phone number is 55, very short phone numbers, and my cat's phone number is 56. All right, and let's pretend that those are both hashing to the same index. Oh man, oh man. Sad. So if it's empty, you can store the thing, 55, and then, okay, my name is being stored there. Keep in mind that you always have to save the key and the value in the table. You store a pair of things, because you're not sure, like, whose number was this, if you just see Lawton there, okay? Because multiple people can map to that same index. Collisions are no fun. So, okay, I want to store my cat's phone number, but, oh man, it's mapping to the same index. I got to find an empty spot. So the easiest way to look for an empty spot is to just linearly try everything after it. Okay, start where we thought we were supposed to put it, and keep trucking as long as you have not found an empty space yet. Just go in order. That's called linear probing. Okay, just add one to the last index that you tried and wrap around if necessary, because you might be taken to the middle of the hash table, right? So here is the mathematical way of specifying that. The first time you're inserting something, I is 0, and so that's just, okay, go to the place that the hash of the key is taking you to, and see if that one's empty. If not, now I is 1, and this will force you to try the next index right after that original one. Yeah, that's how you use linear probing, and you're going to keep going. Make I2 if you still didn't find room to place the next thing. So linear probing, we'll put this here. My cat's phone number. Okay. That is one way of doing things, but if you have a bunch of collisions taking you to like index 0, then I think you can imagine that your hash table is going to start looking like this, with a bunch of indices all huddled near the top, because that's where you got to keep fighting in the next index, and you're just going down like that. So you don't have a lot of empty spots all right next to each other. That's no fun. A way of solving that is to jump around the hash table when I is 1 and I is 2. So that one way of doing that is using a quadratic equation, right? So that is where quadratic probing comes from. You pick 2 constants, C1 and C2, and you just roll with those, and that's going to let you jump around because these are going to become big values when I gets large, yeah? And it'll eventually wrap around in a weird way. So like if you're taken here the first time, maybe the next time you jump here, then way over here, and then maybe down here, and then maybe back to the middle. Quadratic probing does weird stuff, which helps you not have a bunch of collisions or have a bunch of filled-in indices in your table right next to each other. Okay, we like that idea. So that's quadratic probing. That's much better than linear probing, but still not the best. The best way of doing this, of solving this where to put the next thing problem, is to actually use a second hash function. This is called double hashing. Okay, you have to use 2 hash functions now, and that gives you the best way of wrapping around the table in weird ways. Okay, so let's pretend that h1 is just our original hash function, because we always had that to begin with. Maybe it's just going to be key mod n for this example, because that's all you need. Just take our keys are numbers in my example right now. Here's my table. 0, 1, 2 again. And let's pretend I'm trying to insert my phone number, and H1 is taking it to 0, and same with my cat's phone number. H1 of 56 is also 0. Okay, that's supposed to be a 1. So here is a second hash function that always works if your keys are numbers. Just pick a prime number, and that's less than n, and create this number out of it, p minus key mod p. That's a valid hash function. That will always work. And that's going to allow us the ability to wrap around our table in a weird way. So here is your formula for the next index to try. Okay? So when I is 0, of course, if it's empty, just use the first hash function. So that's going to let me put what I wanted in the first index. That's all well and good. And now we have a collision when I'm trying to insert my cat's phone number. Okay, so here's what's going to happen. We then go to our second hash function. Let's say that H2 for 56, because it's the same key, right? Let's say that that is equal to 2. Okay? And so now the next index that I try is purely based on the key itself. Like, it'll be a different way that I wrap around the table for each different key. Isn't that neat? So that's why double hashing is the best. So apparently this is going to take us, when I is 1, to 0 plus 1 times 2 mod n. So that's going to take us to index 2 now instead. And we'll insert Lonzo right here. Okay, hope that makes sense. The reason double hashing is the best is because it provides you a different way of wrapping around the table depending on that key, right? Because we're using that to control how we move around, okay? Which is different to quadratic hashing. I'd be happy to talk about that more in office hours, but this is all we need right now, okay? And yeah, the cool stuff that we're taking out of this from this class is that because we can use prime numbers in this kind of way, it's actually guaranteed, that second hash function guarantees double hashing to visit each index of the table in a different order for each different key. That's really cool. One final problem that you might run into is maybe your hash table is full. Like, you've used all the indices. In your implementation, you're going to have to remember to stop looking once you've visited n different elements, where n is the size of the table. Make sure to watch out for that, because otherwise you'll just keep on trying forever. We don't want that. Okay? You're wrapping around in a weird way, so you're not really sure when you're done unless you count how many times you've looked. Hopefully that makes sense. So that is inserting stuff in a hash table in a nutshell. Removal is kind of unfortunate because that ruins the way that we search for things. Okay? So here is another example of a table. And let's have it have 4 indices, because why not? 0, 1, 2, and 3. And let's say that we have it filled right now with 2 things, like, I don't know, and 7 is like M or something. I don't know. So here, here's me, and here's my mom's number maybe. So let's also pretend that there used to be somebody else's number right here, but we deleted it. I don't know. Let's store my dad's number or something. But we deleted it. And the issue with removal, when you delete something, you have to mark that you deleted that thing. Because otherwise, say that the hash function for my phone number, for number 6, takes you to 0 first. If you go there and you deleted something and you see now that it's empty, you're going to think that my phone number did not exist in the table. Do you see that? You'll think that it didn't exist if you removed something, unless you're careful. Okay, because now it's empty. It would only have been empty if we didn't put the number in, right? No, with removals, everything gets ruined. So what you do is, because of this problem, right, you'd always stop searching when you see an empty spot and think that it wasn't there. We need a second kind of emptiness. Do you remember this from your 41 textbook? So you have to tag each element of your hash table as either, oh, this has been empty since the start, ESS, or this has been, this is now empty because I removed something. Empty after removal is the fancy term, right? And then these are all filled, right? F for filled, let's say. You got to tag each index because when you see this, empty after removal, that means that the thing that you're looking for may be later in the table. You got to keep looking. You see that? So that's where enums come into play. Every index of our table is going to have a status. These three are the possibilities. Okay? So that's, I had to build up a lot of information to get right here. That's essentially what we're going to be implementing. Okay, so remember that, and that's how it works. So let's just go over in a nutshell. Definitely go back to your 41 textbook. Let's talk about, just at a high level, what you need to do when you're implementing this stuff. So if you're inserting something into a hash table, you, using your probing strategy, just keep on hopping around until you find the thing that you're looking for. So you need to, maybe you're taken right here the first time, but you see it was empty after removal, so you got to try a new, you can put something in there now, that's fine, or you can put something in an empty since start index, right? But if it's been filled, like maybe this one's filled and this one's filled, you got to skip it, okay? The empty ones you can replace for insertion, either kind of empty. But hop around until you find something like this one, or this one, that is empty, okay? And then put the value and the key there. Got to save a pair. That's insertion. And then removal, right, is you search for the key. So do the search process. Once you find it, hopefully you found it, you change the status of that index from, okay, 42L or whatever. It used to be filled. You change it to empty after removal. Okay? So that when you search through this spot again, you know that I can rewrite this. Totally fine. Okay? So that's the key. And then search. This whole process is based around searching, right? Searching or looking up things. And removal made that hard for us, sadly. But it's not too bad. So what you do is you just start hopping around until you find either, right? Maybe let's just pretend we're doing easy probing strategy. So 42L, it's filled. Then we have, maybe we look here next. It's empty after removal, which means that the thing we're really looking for might be somewhere later. So then we look here, and maybe we see empty since start. The second you see that, you know that the thing you were looking for was not there. Otherwise, you found it. Okay? So hop around until you find either a filled element with the key that you're looking for. Maybe you're looking for 42. Or you find empty since start. If you were taken to an empty since start index, that means that the thing that you were looking for, even if it, like, no matter how you got there, it would have been filled with that number that you were looking for, right? That means we definitely didn't find it, okay? When you see empty after removal, you want to keep looking, because that means that somebody, maybe the thing you were looking for, who knows, got removed, and things were placed after it as far as the probing strategy is concerned, okay? You gotta keep looking when you see this kind of tag, and of course keep looking when you see a filled element with a different key, okay? Finally, if you have filled, or if you've looked through the whole table, and you haven't found what you were looking for, and you haven't seen empty since start, then maybe the table entirely was full of different things. So stop looking once you visited every node in the table, and you didn't find what you were looking for. Okay? So that's the high-level idea of how to search through a hash table. Definitely yell at me. Check your book, your 41 book, that is, if you have any questions about this stuff. Yeah, so that's essentially your lab. You're going to do double hashing, and I've implemented a lot for you. Let's just look at the write-up very briefly, because most of this stuff was in the slides. These are the files that you'll get, and you're going to be working in hashmap.cpp. Okay, the name of the type that we're implementing is the hashmap class. Okay, and we're hard coding the types of the keys and values. So ints are the keys, so that allows us to make that very cool prime number based hash function, and then strings are going to be values. Okay, So here is a nice resource outside of a textbook, but definitely use your CSCI 41 textbook to guide you as you implement this. And yeah, I have made all the tests for you already. Just get those working and that will be your grade. Okay, so the only thing that you'll be turning in is hashmap.cpp after you implement it. So let's look at hashmap.h right now. So here's our status. So everything that you're putting in the hash table is a hash table item. All right, it stores a key, a value, and a status. The default is empty since start. Yeah, that makes enough sense, I hope. And so here's how you make a hash map. So the constructor makes a table with the given requested size. Here is an insert a key value. See if something exists in the hash map. Go to that index and get back a reference to that thing that's there. You'll throw an exception if you couldn't find the thing. And then remove the value at a given key. Okay? And there's a bunch of helper functions to do all that, right? We have our hash functions. Because we're going to be looking for prime numbers, we'll have an isPrime function, so you can just copy that from your first lab 0. Here's a helper function to find an empty index in the table, and here is a helper function to help you find the index in the lookup table, because it's always a vector, right? Or an array. It's a vector of hash table items. That's our underlying hash table data type. And this helper function finds the index into that vector of a key that you're looking for. Okay? And then also, you'll calculate that special p from that second hash function, and you'll just use that forever. It's you'll search for the next prime number smaller than the size, okay? The size of the hash table that's given to you in the constructor, okay? That will make a lot more sense when you implement it, though. Oops. Boop. So here's hashmap.cpp. You will be following all the fix-me's, okay? So we make a table of a certain size, and then you'll find a good p. Find the first prime number smaller than size using your helper function isPrime. Okay? And then I've implemented the two hash functions for you. You will find the empty index using the probing strategy, right? Just start a loop, set I to be 0, keep on trying, see if you can find something or an empty index. And then index of key, again using your probing strategy, look for the a key in the hash table. See if you can find it. It will be filled in, right? You'll look inside of your table and find a filled location with the key that you're looking for. Okay? And so insert's based around that. Exists is based around that. At is based around searching. You just finally give back the value that you found, right? You'll go inside of the hash table item and do all that. And then hashmap remove, even though it ruins everything, it itself is quite easy, right? All you have to do is find the key you're trying to remove and set its status to empty after removal, right? So not a whole lot of things for you to implement, but it's a bunch of things working together, right? So just remember how that's all working, ask me questions about it, and you will have a functioning hash table by the time you finish this lab. So yeah, I think that's all I wanted to say. You'll only be turning in hashmap.cpp. Do yell at me if you have any questions, and this will be due week 10. Okay, so good luck, and I will see you next week.